those 2 points. This afternoon session, we are happy to say is being sponsored by Consulting Engineers Partnership Limited, who've jumped in to assist to make sure that we could get everyone in this afternoon. We have a very well subscribed session this afternoon. And obviously it is a topic, and the speaker, we all know, is very knowledgeable, and we look forward to the information that will be imparted. So just to give you an idea of how the session will run, we will have the presentation by Engineer Gibbs. That will then be followed by a question and answer segment. When we get to the question and answer segment, I will invite you to field your questions either by raising your hand in the Zoom platform, or if you are camera shy, you can post your questions in the chat and I can relay them to Engineer Gibbs. Okay. Just to give you some introduction into the topic this afternoon, this information is taken from the University of the West Indies Seismic Research Center. And it says Eastern Caribbean earthquakes. The Eastern Caribbean is an example of an island arc system formed at a convergent plate boundary, more specifically at a subduction zone where 2 tectonic plates meet and the denser plate is forced beneath the lighter plate. This is the main cause of volcanic and seismic activity in the Eastern Caribbean. For your general knowledge, the Seismic Research Center operates a network of over 60 seismic stations strategically positioned on islands throughout the Eastern Caribbean, with access to approximately 100 from other regional agencies. Continuous data from nearly all stations is transmitted directly to the office in St. Augustine, Trinidad for real-time processing and analysis. Earthquakes which produce seismic waves are monitored using seismometers. These instruments, which were first used to listen for ground vibrations from nuclear testing during World War II, operate on the principle of inertia. A series of suspended and balanced pendulum-like masses remain stationary but move when the Earth vibrates. The vibration is then recorded on a seismograph as a series of wave motion lines called seismograms. When multiple seismic stations record the same earthquake event, it is then possible to calculate the location of the event using the principle of triangulation. So that just gives you a little background into the topic that we'll be looking at this afternoon. In terms of earthquakes in the Caribbean, Caribbean has recorded earthquakes as far back as 1690 with a magnitude 8 event in around Antigua, St. Kitts and Nevis. Coming through the last 300 years to more recent events we would be aware of, where we would have had earthquakes occurring in Haiti, and that was in, sorry, let me just pull it up here, 2010. That was a Category 7 event which caused extreme damage. We have had another event again in 2018 in Haiti. We've had earthquakes in Puerto Rico in 2020, Jamaica, Cuba, Cayman in 2020, and 2021, a 7.2 event again, Haiti, which caused severe damage. So the region is certainly no stranger to these seismic events. So this afternoon, we'll be discussing the topic of conceptual designs of buildings and earthquakes. And this afternoon session will be delivered by none other than the Honorable Mr. Tony Gibbs, engineering fellow, and certainly a mentor to many who may be logged on here. And I want to extend a special welcome to our friends and colleagues who are joining us from outside of Barbados, those who are joining us from throughout the region. I'll just give you a brief background on who Engineer Gibbs is, and then we'll turn the session over to Engineer Gibbs. Engineering fellow, the Honorable Tony Gibbs was born in Grenada, and he went to 10 schools in 4 Caribbean islands, Grenada, St. Lucia, St. Vincent, and Trinidad, before attending 2 universities in Northern Ireland and England. and he lived in two more Caribbean islands, Jamaica and Barbados, the latter being his home since 1965. Engineer Gibbs headed the firm of Consulting Engineering Partnership Limited in Barbados from 1965 to 1996, during which period he was responsible for over 1,500 projects in the Caribbean, including such notable buildings as the Life of Barbados building in Wilde, Central Bank and the Frank Collymore Hall, the General Post Office, Grantley Adams International Terminal Building, Phase 1 in 1979, the Control Tower at the airport. Other projects Engineer Gibbs have been involved with of note outside of Barbados would be the Eastern Caribbean Central Bank Building in St. Kitts, Government Headquarters in St. Vincent, Police Headquarters in Antigua. And this is just a sprinkling of buildings, but these are key buildings that persons would probably recognize in various areas around the region. Mr. Gibbs' special interests are in the fields of collaborative design in multidisciplinary teams and designing against the natural hazards of hurricanes and earthquakes. This work has taken him to assignments in China, Indonesia, Oman, Egypt, Tunisia, Kosovo, and every country within the Caribbean. He is particularly interested in the interrelationship between engineering and insurance and has assisted RMS of California and AIR of Boston with the development of their Caribbean loss models for earthquakes and hurricanes. Without further ado, I would like to turn this session now over to Engineering Fellow, Mr. Tony Gibbs. Over to you, sir.
First, let me share the screen, should I? Share the screen. Can you see the screen?
Yes, sir.
Okay, well, good evening, colleagues. The subject is conceptual design to resist earthquakes. This has as much to do with architects as engineers. It's interesting that we are doing this talk in April, because April, I'm trying to move my slide forward. Let me see. Because April is one of the particularly dangerous months for earthquake occurrences. The other dangerous months are July, January, September, November, May, March, June, December, October, August, and February. So let's start with some general issues. The common shape characteristics for earthquake-resistant design are the favorable ones on the left, the favorable plans and elevations, and unfavorable or complex plans and elevations on the right. Redundancy is a characteristic which is very important in earthquake resistance. On the screen, there are plans of two identical shape and size buildings. The one on the left is supported by 4 strong enough columns to resist the forces. On the left, on the right, the same building, same size of building is supported by 16 columns. The building on the left has very little, if any, redundancy. The collapse of one of those columns would probably lead to the dramatic collapse of the whole building. Whereas the building on the right has a lot of redundancy, the failure of an individual element would not lead to the collapse of the whole building. Now, those in the audience who are of the Islamic faith would recognize the difference between the two, because in the Islamic faith, there's in the marriage situation, you can have 4 wives, whereas us of Christianity can only have one wife at a time. So we have little redundancy in our marriage lives, whereas people of Islam would have a significant amount of redundancy. In Chile, in 1960, there was an earthquake which was the largest ever measured since measurements began in 1899. The magnitude of that earthquake was 9.5. That's a magnitude. More recently, in Canterbury, in New Zealand, there was an earthquake of magnitude 6.3. Now, a 9.5 magnitude earthquake has 27,000 times the energy of a 6.3 magnitude earthquake, 27,000 times the energy. Nevertheless, that relatively small 6.3 magnitude earthquake in Canterbury, New Zealand, generated vertical accelerations equivalent to twice gravity and horizontal accelerations just over gravity. The twice gravity vertical accelerations had never previously been recorded. Windstorms and earthquakes and actually most natural hazard events are open-ended phenomena. There must be a realization that there's a real risk that design forces may be exceeded. And this is particularly so in the case of earthquakes, where, largely for perceived economic reasons, the design force is deliberately determined to be less than that expected during the anticipated life of the building. This leads to a requirement for redundancy in the structure and for toughness, the ability to absorb overloads without collapse. This diagram demonstrates our predicament. The actual demand of the earthquake itself is the top graph. That's what the earthquake is imposing on the structure. Our codes and standards tell us we should design for the bottom graph. Those are the loads in our codes and standards. Now, many of our buildings have accidental overstrength, so the actual capacity of our buildings might be a bit more than is determined by the code. So the actual capacity is the dashed line. There's still a huge gap between the actual capacity of rail structures and the actual demand of the earthquake. And that huge gap is bridged by the characteristic of ductility in our structures. The other issue of great concern to earthquake engineers is the soils. On stiff soils like rock, buildings which have high natural frequency or low natural periods would suffer a lot. And the buildings with a low natural frequency or long period, natural period, would suffer much less on rock. The opposite happens if the structure is founded on soft to medium clay and sand. On soft to medium clay and sand, the low frequency, long period structures suffer quite a lot. And the gap can be demonstrated. If you look at the line for frequency of 1 hertz or period of 1 second, you can see the huge gap in damageability of buildings on rock, with the blue line, and buildings on soft to medium clay, the red line. Those graphs were from a study by Professor Bolton Seed, that's the father, the son has the same name, Bolton Seed, and of the observations from the Caracas earthquake of 1967, July. So soils are important. And so the soil structure interaction, which has to be considered for different characteristics of buildings and different characteristics of soils. This is a critical aspect of earthquake resistant design. So the soils investigation is an important ingredient in preparation for designing any building for earthquakes. In the case of hurricanes, if you have an intact envelope to your building, inside the building is not impacted at all. In the case of earthquakes, everything is impacted. Everything inside the building is impacted, as well, of course, as the external frame of the building. And that's a big difference. The examples of non-structural components which are affected by earthquakes represent the majority of the cost of most buildings. Those non-structural components include electrical and communication systems, the roof covering, the lighting system, air conditioning, various pipes in the building, parapets, ornaments, railings, attachments, doors, partitions, furniture, windows, the plaster, and the ceilings. All of those things which make up most of the costs of a building are non-structural, but they are impacted by earthquakes. And that means that there's a real need for electrical and mechanical engineers and architects to pay attention to earthquake resistant design. Special attention must be paid to fragile partitions in critical areas such as hospitals and exit routes in buildings. If the partition, as in the case of this hospital photograph, is made of glass, brittle glass, and it breaks during an earthquake, that causes much confusion in the hospital itself. The other element which routinely fails in earthquakes is suspended ceilings. There's one manufacturer that I found, Armstrong, that produces suspended ceilings specifically for earthquake zones. I haven't found any other so far. And those suspended ceilings need to be adequately braced against horizontal motions, and the various other systems like lighting systems and air conditioning, ventilation systems, which are attached to those ceilings, need to be well supported by strong enough hangers, because there's also a significant vertical component to the earthquake motion. It doesn't matter much, you may say, if a bookshelf falls over. It might fall on someone, but in any case, it causes much disruption and necessitates the use of human resources for cleanup when they are required for priority tasks in the aftermath of an earthquake. So bookshelves should be braced against toppling, and the contents of shelves should be restrained from falling or sliding off of the shelves themselves. And then there's a cladding on the outside of buildings. Professor Hausner, the father of modern earthquake engineering, was once asked, "What should I do if I feel the earth shaking?" And Hausner said, "If you feel the earth shaking, stay where you are and count to 100. When you get to 100, the earthquake will be finished and you can walk calmly out of the building." What he was alluding to was the danger of rushing out of buildings when there's an earthquake on, because cladding and shards of glass from broken windows are falling on the pavements adjacent to the buildings. It was once estimated that the most dangerous time for an earthquake to occur in San Francisco was when the offices were closing at 5 o'clock, because then the pavements would be full of people and the glass would be falling as shards on those people, And there could be as many as 10,000 deaths caused by that. Now, we have joints in buildings, and we have to have joints in many buildings. And the architectural components that run across seismic joints must be correctly detailed. What used to be the Holiday Inn, which was opened in 1974 in Port of Spain, and is now the Radisson, has a 200 mm wide joint running from the roof to the foundations. The building has a corridor running right through the building, which includes bedrooms on both sides. You're seeing bedrooms on one side, on the other side of the building there's an equal number of bedrooms, and those bedrooms have between them a corridor running the whole length. There are 10 bedroom floors, and that corridor has, of course, a ceiling. And the ceiling was initially detailed to be continuous across the joint. And the first earthquake to occur after 1974 caused great alarm because it seemed as if the building was falling apart. So we were called in to do a report on it, and it was obvious that the building was not falling apart, and we explained what was happening. They replaced the ceiling in the same way. And there were 3 other events which caused that ceiling to break in the same way after the first event. In the first 2 of those 3 events, we were called to do reports, and our report was the same as the previous report. Of course, we got paid 3 times. We got paid 3 times for doing 1 investigation and producing 1 report with different dates. The 4th time it happened, they did not call us because they were now cottoned on to the real reason why the ceiling was breaking. They did not call us. In fact, there was a press release saying there was nothing wrong with the Radisson Hotel. It was just the ceiling going across the expansion joint. And there's a photograph taken of the 4th event and the pieces of the ceiling falling on the floor of that particular corridor. So anything going across an expansion, a seismic joint, has to be flexible or has to be detailed so it can accommodate the motions across that seismic joint. Many buildings are structured with beams and column frames, and many of those buildings have rigid partitions and rigid walls which are plugged in between those columns and beams. And that causes an invalidation of the analysis of the frame and causes a different distribution of loads overall on the building and can cause significant damage or collapse. So rigid partitions and walls should be separated from the adjacent beams and columns. This is not difficult to do and should be done. Now let's talk about the relationship of architecture and engineering. In the words of Geoffrey Wood, one of the 5 founding partners of Ove Arup and Partners, earthquake-resistant design is rarely a problem for architects. Buildings are designed by architects and engineers. In reality, in most cases, buildings principally for human occupancy are designed conceptually by architects. That is to say, that architects are the ones principally responsible for the configuration of buildings for human occupancy. Configuration encompasses architectural shape and size, type, size, and location of structural elements, type, size, and location of non-structural elements. So, the architect determines those overall shapes. Configuration has to do with the shape and size of the building. Inevitably, shape and size to a large extent determines or greatly influences the type, shape, arrangement, size, location, and most other aspects of the structural concept. Irregular structures such as this usually require dynamic analysis, which is much more difficult than static analysis. Now, either the architect has a better than usual knowledge of the basic principles of the conceptual design of earthquake resisting systems, or the architect should involve the structural engineer in the initial discussions and development of the building concept. This is what we did. When Mervyn Awan and I were approaching the design of the Central Bank of Barbados, we spoke for 2 weeks before Mervyn put a line on the drawing, on his drawing. 2 weeks discussions. At the end of it, Mervyn understood what was good and what was favorable from what was unfavorable. The extra over costs of providing earthquake resistance to the Central Bank of Barbados was approximately $0. The Tri-Service Manual of the USA Army, Navy, and Air Force states, a great deal of a building's inherent resistance to lateral forces is determined by its basic plan layout. Engineers are learning that a building's shape, symmetry, and its general layout developed in the conceptual stage are more important than the accurate determination of the code prescribed forces. Geometry trumps mathematics. Some of the buildings have very irregular in-floor plan. And if you have that situation, you can correct the situation in your conceptual design by separating those irregular structures into a series of regular structures by including seismic joints. And those seismic joints have to be wide enough to prevent the hammering of one part of the building against the other part of the building. The taller the building, the wider the joint. The 15-story Radisson Hotel in Port of Spain required a 200 millimeter wide joint. If you go to the Eric Williams Medical Science Complex in Trinidad, you will notice that they don't have tall buildings there, but the 3-story buildings have wider joints than the 2-story buildings. The people knew what they were doing. Structural engineer William Holmes, writing many decades ago, stated, it has long been acknowledged that the configuration and the simplicity and directness of the seismic resistance system of a structure is just as important as the actual lateral design forces. So here we have illustrations of discontinuities. In illustration 1, the gable end shear wall is discontinuous. It does not go down to the ground. It's missing from the first story. In the second illustration, the beams at first floor level are discontinuous. They don't go through to the corner column. And in the third illustration, there are columns in the superstructure from first floor to the roof, which don't go through to the ground. Those discontinuities are red flags, which need to be treated with great caution. Henry Degenkolb, famous earthquake engineer of California, now deceased, was emphatic in stressing the importance of configuration. He said, if we have a poor configuration to start with, all the engineer can do is to improve a basically poor solution as best she can. Conversely, if we start off with a good configuration and a reasonable framing scheme, even a poor engineer can't harm its ultimate performance too much. And this last statement is only slightly exaggerated. So there are illustrations of abrupt changes in lateral resistance and abrupt changes in lateral stiffness. Now, those quotations above warrant discussion among the various disciplines involved in the design and building processes. Terran, a Nicaraguan architect, recommends that buildings be simple, continuous, symmetrical, straightforward, and repetitive. This advice is given not as an absolute, but as a qualitative factor that influences the reliability of the structure. Terran, an architect, asks for understanding and knowledge among the disciplines, not the imposition of mandatory constraints. Let's look at some specific conceptual design issues. Those three buildings are square. Externally, they seem extremely simple and uniform in geometry. However, in each case, the symmetry is false. In the case on the left, the false symmetry is brought about by a stiff shaft for elevators and stairwells. In the middle diagram, the lack of symmetry is brought about by stiff shafts for services. And the one on the right has party walls on two sides only of that building. So in all of those cases, we end up with significant lack of symmetry, although the building on plan is very symmetrical and square. Now let's look at another aspect. In addition to horizontal and vertical forces, engineers impose torsional forces on buildings. And torsion is best and most efficiently resisted by having the resisting elements as far from the center as possible. So those two buildings on the top, similar in size and shape externally, have their resisting systems different. In the one on the left, the resisting system is a central core, which is a very efficient way of dealing with the horizontal loads, but not with the torsional loads. The building on the right, the upper right, the resisting system are 4 shear walls on the perimeter of the building. That's much better for resisting torsion. Now look at the round building on the bottom. You'd never guess where that building is. That building is not in a seismic zone. It's a perfect shape for seismic resistance, both horizontal as well as torsional forces. But that building is the Ariel Hotel at Heathrow Airport in London. But it's an ideal shape for earthquakes. So bring on the earthquake at Heathrow Airport. And then there's irregularities in elevation. Those are obvious. So the best building is a pyramid, a Giza pyramid in Egypt, or pyramids as illustrated there in Indianapolis, but not the inverted pyramid in Dallas. One of the most dangerous types of structure in an earthquake is one with soft stories. In 1999, during the Izmit earthquake in Turkey, there were 18,300 deaths. Almost all of the deaths were in 6-story buildings where the bottom story, the ground floor, was opened up for garages and shops, and the upper 5 floors were closed up with walls and partitions as domestic accommodation. One of the 18,300 deaths was a close friend of my then secretary at CEP in Barbados. She happened to be visiting Turkey, and she spent 3 days at the site of the collapsed building, assisting to get the friend out. The friend was eventually rescued, but only the only way they could get her out was to amputate one of her legs. And her 6-year-old son died in the earthquake. So soft stories have to be avoided. Now, what is a soft story? A soft story is a story which is more flexible than the one above it. Most soft stories are the ground floor, but you can get a soft story at mid heights of a building, as illustrated on the right of this diagram. The Macuto Sheraton Hotel in the northeast coast of Venezuela had a soft story. And in the 1967 earthquake, all of those massive columns failed in share, but the building did not collapse. After the earthquake, there was much discussion about whether the building should be demolished. They decided not to demolish the building, but to install shear walls between the columns. So if you went, I presume the hotel is still there, it probably isn't a Sheraton anymore. I stayed at it many, many years ago. And when I stayed at it after the earthquake, you could not see this open area at all. This open area was now a series of offices and shops closed up with shear walls between the columns. And there is the incipient failure of a building with a typical soft story situation, shops at the bottom, domestic accommodation above. So domestic accommodation has many stiff walls and partitions, and the shops below are wide open spaces. And there are ways of dealing with this. Ideally by adding columns or by having super bays. A super bay is one where every other bay, the beams are not rigidly connected to the columns. So the tall columns, bay at the bottom is replicated by tall bays above. Examples of structures with irregularities of elevation. A, that's obvious, geometrically obvious irregularity. B shows a situation which does not look irregular, but some of the floors have very heavy equipment, and those concentration of loads, concentration of masses, will produce irregularities. And then in C at the bottom, the large differences in the stiffness of the stories produce the irregularities. To be provocative, you would say that there's a need for the beams to be weaker than the columns. But it's safer, it's more acceptable to say that the columns need to be stronger than the beams. We need failures to occur in the beams and not in the columns. So wherever beams are connected to columns, the failure should be in the beams. So the building on the left is how we want it to behave. By failure, I mean exceeding the elastic limit, because you have to exceed the elastic limit, go into the plastic phase, nonlinear phase, to absorb the energy of the earthquake. Bearing in mind from an earlier slide that the earthquake forces are much higher than the code forces. So you get failures in the classical sense of failure, the exceeding the elastic limit. So you exceed the elastic limit, you go into the nonlinear phase of the material, and that absorbs the energy of the earthquake. So those failures must be in the beams, not in the columns. If they're in the columns, as in the right-hand side of the slide, you can have dramatic collapse. Now, the major forces in an earthquake to be resisted are the horizontal components of the force. In an earthquake, you have vertical forces, horizontal forces, and torsion. You have 6 degrees of freedom. Now, the horizontal forces are resisted by vertical elements, shear walls, braced frames, and moment resisting frames. And you need a diaphragm, usually made up by a floor slab, to transmit and share those loads among the various vertical elements. So that diaphragm, illustrated at the bottom of the slide, is in fact a horizontal beam. Now, if you have a beam, you chop out a huge gap in the bottom of the beam, you no longer have a good beam. But we chop out huge amounts from our horizontal beams, which are called floor slabs or diaphragms. And when you do that, you have to make sure to get the loads around those holes that you have created to accommodate elevators and vertical stair shafts. Different structural systems are used for taller buildings. From A to E, frames are A, B, shear walls, C, shear walls with boundary elements, D, confined shear walls, and E, braced frames. Now, moment frames are provide the greatest flexibility when it comes to the functional planning of buildings. That's positive. However, they exhibit greater deflections than shear walls and braced frames, so the detailing of non-structural elements becomes more problematic. And that's a negative characteristic of moment frames. Seismic resisting systems can have either unbraced frames or braced frames. And if you have braced frames, they can either be concentric bracing or eccentric bracing. Eccentric bracing is where the braces do not end up at the junction of beams and columns. So eccentrically braced frames are deliberately used so as to produce a link between where the brace ends on the beam and the adjacent column. And it's in that link that we are expecting the failure or the exceeding of the elastic limit to occur. And those links become the elements, the parts of the structure to absorb the energy from the earthquake. Materials. The desirable features for structural materials for earthquake resistance are high ductility, high strength to weight ratio, homogeneity, and ease in making full strength connections. All of those characteristics are eminently existing in steel structures. Steel behavior. The material is inherently ductile. Bear in mind that the ductility of the overall structure is usually less than the ductility of the material itself. And then there's damping. Welded structures have low damping. More damping is achieved in bolted structures due to the slippage at connections. Now, slippage doesn't sound like a good thing, but it is a good thing because it produces damping. The primary energy absorption is the yielding of the members exceeding the elastic limit, going into the nonlinear phase, and the area under that stress strain curve is a measure of the amount of energy that is absorbing. Now here's an interesting retrofitting technique. In this case, the retrofitting of the moment resisting frames is done the ductile fuse in shear at midspan, produced by a specially braced rectangular opening in the web, instead of modifying the beam to column connections. So you're moving the plastic demands, which are what is used to absorb the energy, away from the critical beam column regions, while ensuring that the frames develop a ductile mechanism. Okay, so that's what we normally do. And that's what all over the Caribbean we aim to do, except in Martinique. Martinique is the only country in the Caribbean with base isolated structures. And there are many. And it's all due to the campaigning over several decades by an architect called Frank Hubert, whose English is not very good. So if you speak French, you can communicate with him. He's been campaigning for decades. The normal performance basis that we usually work on is for the most important structures, like referral hospitals, we require them to be fully operational for frequent earthquake events, to provide immediate occupancy, but not be necessarily fully operational for the design earthquake, and to be safe against loss of life and loss of limb for the maximum considered earthquake. The medical facilities, medical community thinks that that's not good enough by any means, because the referral hospitals have their greatest demand immediately after a major earthquake. So in October 2004, there was passed a regulation or an advisory clause in Washington, signed by all the ministers of health of the Americas, from Alaska in the north to Tierra del Fuego in the south of Argentina, including Barbados, Trinidad and Tobago, Jamaica, and all of our islands. And that document, which was signed by those ministers, said that referral hospitals must be so designed, constructed, and maintained that they remain fully functional in their own infrastructure immediately following major earthquakes and hurricanes. Now, that phrase, in their own infrastructure, means they must not be reliant on the municipal water supply, on municipal electricity supply, and even on the municipal telecommunications. They must be self-sufficient, and must be able to treat all patients, both those who were in the hospital before the earthquake and those who come into the hospital after the earthquake, by being fully operational, fully functional. I doubt whether the ministers of health of CARICOM understood what they were signing in 2004. But the document is there on the internet for all to see. So let's talk about base isolation, which is the only economical way of doing what that document wants us to do. That's base isolation. Base isolation is ideally removing the building from the ground. You need strong trees with strong trunks, strong branches, and a strong rope, and you hang the hospital from the branch. Straightforward, isn't it? Okay, but base isolation is not a new concept. The first evidence of base isolation for earthquake protection is in Pasargadae, a city in ancient Persia, which is now Iran. The tomb of Cyrus is the burial place of Cyrus the Great of Persia, who lived half a millennium before Christ, and he was the founder of the Persian Empire. And his tomb was supported on dovetail staples, which were allowed to swing from left to right and provided some flexibility, some resistance to earthquake damage of his tomb. And then there are the ancient Greek temples, Chinese monasteries, temples, and bridges, as well as temples erected in Italy in the past, and they appear to be protected by seismic isolation systems. How else will those unreinforced masonry structures still be standing in areas where have relatively frequent earthquake activity? They appear to be located on sand beds, and on top of the sand bed is placed the fleece of sheep, and that's the base isolator. Now, at the top of that slide is something in Latin, and not many of you these days can read Latin. I did 9 years of Latin in school. That's why I'm an engineer. So my wife, who is a foreign linguist, has translated it for me. So this is her translation. Gaius Plinius Secundus, writing in the Naturalis Historia, stated, "A true wonder of Greek magnificence, the Temple of Diana of Ephesus, built 120 years ago or 70 years before Christ, stands out in the whole of Asia Minor. In the ground, they made it swampy, lest it feel the movement of the ground or cracks might appear in the building. Moreover, so that the millstone foundations not be placed in a slippery or unstable position, they had trampled down fleeces of wool, and these remained underneath the foundation stones." So that was the base isolation technique used for Diana of Ephesus. The only base isolated building I know of in Barbados was built in the 19th century. It is the old, magnificent headquarters of Barbados Mutual Life Assurance Society at the bottom of Lower Bay Street. And that building, built in the 19th century in Bridgetown, sits on a whole year's crop of Sea Island cotton from St. Kitts. It's base isolated. So how does base isolation work? The main properties of a base isolator is to resist vertical loads of the superstructure. It has to have high lateral deformability, high energy dissipation, and has to have recentering devices to bring everything back in place after the earthquake. The behavior of base isolated structures differs significantly from fixed base counterparts because of the elongation of the vibration period and the increment of the structural viscous damping. So we start off with a spectrum, and we have to move from A to B. We have to lengthen the period. By lengthening the period, we move into a part of the spectrum which has lower acceleration. So that's the first thing we do. The second thing we do is to increase the damping. And that is diagrammatically illustrated by dropping the spectral diagram. So when you combine the two things, you move from A to B by elongating the period, and from B to C by increasing the damping. And that's what base isolation is doing. So in the top right-hand corner, you'll see a building on a shaking cable. There's a close-up of the base isolator in the bottom right-hand corner. And you would notice the diagram on the left that the base isolated structure does not deflect nearly as much as a fixed base structure, and therefore the protection of the non-structural components is secured. Now the base isolator, the most common type, is one which is made up of a multi-layer sandwich of rubber and steel, as you can see in the cutout model on the upper left-hand corner of the diagram. And bass isolators come with music, calm the nerves during an earthquake. The ground is moving at the bottom, and the building above along the middle. Now, here we have the difference in behavior, a fixed base building on the left, base isolated building on the right. I'm sure all of you would prefer to be in the building on the left. That's far more exciting than being in the building on the right. If you're in the building on the right, you may never know the earthquake has occurred. You'd have missed all the fun. Another way of dealing with the earthquake forces is energy dissipation. If you look at the building on the lower right-hand corner of the screen, you see it's moving, it's on a shaking table. In this case, the energy dissipation devices are in the superstructure. I repeat that so you can see the motion. You can see it moving on the shaking table. One type of energy dissipator is illustrated here. Those yellow steel plates have a particular shape which allows them to go into the plastic stage at a very early stage when the earthquake occurs. And those plates, in fact, absorb the energy of the earthquake. And that technique was being used in this particular illustration in the central offices of the Social Security Institute in Mexico City after the 1985 earthquake. I took that photo. And then there are the mechanical devices illustrated here, elastic plastic dampers, load limiting devices, shock transmitters, viscoelastic dampers, and viscous dampers. This is mechanical engineering helping us structural engineers. And this is a viscous damper in action. Sorry, no music this time. And that, my colleagues, is all that I have to say this evening, unless I have questions to answer.
Okay, thank you very much for the impressive presentation, Engineer Gibbs. We would now like to turn the floor over to those participating in the event to ask Engineer Gibbs some questions. You can either do that by raising your hand or putting the question in the chat. So I can see that we have Mr. Frederick Johnson with a question for you, Engineer Gibbs. Mr. Johnson, you can unmute and ask your question, please. Hi, Mr. Johnson, you can unmute and ask your question, please.
Okay, can you hear me now? Can you hear me?
Yes, we can. Yes, we can.
Okay, great, fine. Terrific sense of humor there, Tony, as well during the lecture. Thank you very much for that. These things tend to be a little on the dry side. Here's my question. Regarding discontinuity, in building design you mentioned before, and you gave us some sketches and drawings there of three-dimensional objects being discontinuous on at least one elevation. Now, here's the question. Regarding the central bank, that has two elevations, one facing north and one facing south, if I get my orientation correct, which are discontinuous to the rest of the structure. And also the Life of Barbados, which is more of a horseshoe type design, again, with a very large hole facing southeast, I think it is. So how does that wrap up with your comments about discontinuity being a red flag?
Well, it is a red flag. But in the case of the central bank, what's wonderful about the central bank is that the sharing of horizontal forces among the 12 towers and the sharing of vertical forces among the 12 towers was very, very similar. Each of those towers took very similar percentages of the horizontal forces as it did of the vertical forces. Also, the beams spanning between those towers, those groups, those four groups, each of 3 towers, the beams were not rigidly connected to the towers. So they did not form a rigid beam column situation. So the discontinuity was very, very minor in that particular case. In the case of the Life of Barbados, that big hole in the front the entire building is glazed, and the glazing does not stiffen the building in the same way as a rigid block wall would do. And therefore, that was not a major issue. It had to be taken into account because in the case of Life of Barbados, there is some stiffness, some asymmetrical stiffness brought about by the elevator shafts and the staircase circulation. And that had to be taken into account. So when you have a red flag, you have to recognize that the flag is red and do something about it.
I've got one more follow-up as well.
In general, I would say the Life of Barbados is not an ideal structural concept.
No.
But the central bank is.
I see. Okay. Could you say something briefly about pendulum dampers on high-rise buildings?
I can't say a lot about it. They are used. There's very good examples of it in Taiwan, for example, and in Japan. What they do is to swing in the opposite direction to the sway of the building. So they kind of bring the build. They reduce the effect on the building of the earthquake. But I don't know very much about it.
Thank you.
Thank you, Mr. Johnson, for your question. The next question to you, Engineer Gibbs, comes from Jonah Sanchez. And the question is, are there any cheaper alternatives to base isolation that have been successfully used, apart from the fleece and the cotton that you mentioned?
Well, actually, base isolation is not expensive. And here's an advantage of base isolation, which I did not mention, but architects should pay attention. You can have very irregular buildings. And the way to deal with them is to have them base isolated. Base isolation solves the problem of very irregular buildings. But studies have been done in New Zealand about the cost benefit of base isolation. And they have found that a base isolated building is no more expensive than a conventional building, and it provides a much better protection against damage in a major earthquake.
Okay. All right, we're going to take another question from the chat, and then we'll have a question from Lucan Robinson. All right, so the next question is from Akeem Brown, and it says, what was the threshold of damage to determine the safety of the hotel that suffered shear damage in the ground floor soft story?
What was the threshold?
Threshold of damage to determine the safety of the hotel that suffered the shear damage in the ground floor soft story. This will be the building in Mexico, I think.
No.
In Costa Rica.
That's in the northeast coast of Venezuela.
Venezuela, right.
In it was a Makuto Sheraton at that time. I don't know what it's called now. I don't even know whether it still exists. I suppose it was a huge hotel, so I assume the building still exists, but I doubt whether it's still a Sheraton hotel. You can see the amount of damage. The columns all failed in shear. You can see that from the photograph. But the earthquake didn't last long enough or wasn't strong enough to cause the building to collapse completely. Those are very big columns, by the way. They're 42 inches in diameter. The building was not a very tall building. I think there were about 8 stories of bedrooms above that main floor. I don't have much detail to answer your question in detail, but there was sufficient damage that there was serious consideration for demolishing the hotel. They certainly could not repair it to allow it to remain architecturally the way it was intended originally. So what they did was to destroy the architectural space that you saw in my photograph by connecting the columns, adjacent columns, across the building and along the building with shear walls, with leaving enough room in the shear walls along the building for doors so people can get in to the office spaces and the shop spaces which were created by cutting up that lovely open space into a series of discrete rooms.
Mr. Sanchez, I see you've raised your hand. Do you want to do a follow-up to your question in the chat? Unmute, please.
Hi, can you hear me?
Yes, we can.
Actually, it's 2 completely new questions, but I want to give an opportunity for the other participants to ask them first, so I could wait a few minutes if that's okay.
That's fine. Thank you very much for that, Mr. Sanchez. Okay, Mr. Robinson, please unmute and ask your question.
All right, thank you. And thank you very much for the presentation. It was an excellent presentation. I'm an architect and I'm curious about 2 things. One, what is the impact of having a basement on trying to do a base isolation building? Let's say the building is 7 stories tall, but you're going to include a basement level. Let's say 2 levels of basement. How does that affect the approach to that design?
Well, the location of your base isolators can be at several levels. The base isolation is usually at foundation level, but you can, in fact, if that's not convenient, locate your base isolators at ground floor level. But what you have to do then is to have very stiff construction, very rigid construction for the basement.
Excellent.
Am I answering your question?
Oh yes, very much so.
I actually have one of the slides which I hid in my presentation shows various options for locating the base isolator. So if you sent me an email, I could send that particular diagram to you.
Thank you very much for that. I'll send the email shortly. I have one quick follow-up question. You mentioned that we cut holes in the diaphragm, which is basically the floor slab. Would you consider then having detached cores, elevator cores, stair cores, as the best solution to not disrupt the continuous slab?
You mean not have the elevator core separate from the rest of the building?
Yeah, think of Lights of London, where the elevator and the stair cores are on the perimeter of the floor slab.
Yes, you can do that. So the elevator core has to be stable in itself.
Correct.
And has to have a sliding connection to the main building, which has to be stable in itself.
Okay.
And across
sliding connection.
Yes, because I mean, if it's a tall building, the gap is going to be quite wide. In the case of the Radisson Hotel in Port of Spain, if you lift up the carpet in the corridor, you will see you have steel plates on both sides of the joint, of the 200 millimeter joint, and they slide in between one another, so that a person with high heel shoes doesn't go through the floor, so to speak. So you have to have that kind of situation. Now you have to be careful. Sometimes the sliding is done one plate on top of another. And there's a case recently in Trinidad at a building which my firm did. It's a building which replaced the Queen's Park Hotel in south of the Savannah, in Queen's Park, Savannah. And there was a sliding connection between two parts of that building. And the maintenance people, without reference to us, literally welded the plates together. And when the earthquake occurred a few years ago, that welding of the plates together caused damage. Likewise, I've seen at the Eric Williams Medical Science Complex that those very nice seismic joints, which were carefully designed by whoever designed the buildings, in some cases, they have plugged those joints with mortar because they don't understand why they should have those joints. So it's a problem of how do we control what is done to a building after we have left the site. It's a real problem.
Thank you very much for that.
Okay, thank you for your question. It's going to go to the chat and then we'll go to Jonas. In the chat, we have a question from George Tambora. What is the commonly used reference or guideline for the design of seismic isolation systems?
Repeat that.
What is the commonly used reference or guideline for the design of seismic isolation systems?
Well, there are many documents which are available. I don't know which are the most common, but the most modern codes and standards now recognize that is one of the options that is used by designers, and there is guidance in that. But in most cases, the information on base isolation is specialized. That does not mean it's difficult, but it's specialized knowledge, and you have to go outside of the normal codes and standards for that guidance.
Okay, thank you. Okay, Jonas, can you unmute and ask your second question?
Yes. Well, it grew into 3 questions, but let me ask it first that are more relevant. The first question is, what level of earthquake would justify the use of base isolation? For example, here in my home country of Belize, we don't have much seismic risk. It's really more concentrated to the southern part of the country, where at most we might experience a magnitude 4, some moderate shaking and cracking. So what's the threshold where you said, okay, I think we need to consider a base isolation?
It depends on how important the structure is. I mean, do you want the structure? I mean, conventional earthquake resistant design assumes damage to the structure when impacted by the core earthquake. The core earthquake will damage the structure, because is that damage to the structure, is that going beyond the elastic limit that allows the structure to absorb the energy of the earthquake in its plastic stage. So the answer to your question is it depends really on how important is it to you not to have damage. Because even the minor earthquakes in south of Belize, there could be a case for having base isolation if, for example, in the south of Belize, you have a referral hospital. I don't know that you do that. As far as I know, there's only one referral hospital in the country of Belize, and that's the Karl Huschner Memorial Hospital.
Okay, thank you. And the second question is, I missed it when you mentioned it because I had a little bit of internet connectivity issues. You mentioned a document that CARICOM signed on that lists, all these requirements. And you mentioned that, buildings of high importance, I suppose, like hospitals and so, they need to be completely independent of municipal services such as water, electricity. What document is that? Because I kind of just missed that, so I'm a little interested in that one.
It's not a CARICOM document. It deals only with referral hospitals. It's a PAHO document, Pan American Health Organization. There was a meeting in Washington in October 2004. And at that meeting, there was a resolution which was signed by the Ministers of Health of the Americas, all the Americas, Canada, the USA, Mexico, through Central America, around the Caribbean, and in South America. They all signed on. They didn't know I don't think they knew what they were signing or the full implication of what they were signing, because the hospitals which have been designed after 2004 in the Americas, very few, if any of them, have complied with that resolution.
Okay, thank you. And then just one last quick question.
But the information on that is on the internet.
Okay, thanks. I think I'll do some research because it just piqued my interest. And the last one, and I saw the picture in the slide. I think it was the hotel in northeastern Venezuela that the columns sheared off, and there was a debate as to whether or not, I mean, ultimately they repaired it. And that's an interesting thing. I mean, most of university and even in my engineering profession, they said, okay, design for earthquakes, make sure it's fine. But I don't seem to have a lot of information. How do you repair earthquake damaged structures? I don't know if you could recommend any references or where to start, how to rehabilitate a building from earthquake damage.
What they did at Makuto Sheraton, they didn't repair it, they strengthened it. I indicated that repairing those columns probably would not have solved the problem. They actually put in new structure, a lot of new shear walls. They destroyed that architecture, the architecture of that space. They strengthened it. How do you repair? The repair is usually a question of strengthening buildings which have been damaged rather than repairing. In a sense, repairing insinuates that you are going to stay with the existing structure and just do something where the cracks have occurred and so on. That can only be meaningful if it's minor damage. If it's major damage, you really have to strengthen the building by adding new structure to it. And that is a case where the new structure could be energy absorbing devices, such as I illustrated in the Social Security building in Mexico City. And I show you several mechanical devices which can be used for that purpose.
Okay, there is, I guess, a bit of a reference offered by Clifford in the chat. He mentions that ASC 7, Chapter 17, deals specifically with the design of isolated structures. So Jonas, you can probably refer to that for some guidance as you do your research. Okay, we'll take another question from the chat, Engineer Gibbs, and then we will go on to Jose Manuel Diaz. This one is from Joshua Olton, and he's saying, great presentation. Earlier, you stated concentrated masses may cause irregularities. However, your diagram showed the entire story having the concentrated mass. Is there any difference if the mass throughout the same story varies? For example, if a building with 3 bays has a mass twice the amount in bays 1 and 3 than that in bay 2.
It sounds as if 1 and 3 are, that sounds as if the mass is symmetrical and that floor, 1, 2, and 3. Yes, those concentrated masses are usually very heavy equipment, bolted to the floor, not able to slide along the floor in an earthquake. And the location of those very heavy pieces of equipment on the floor can cause a torsional response of the building because of their lack of symmetry on the particular floor itself.
Okay, thank you, Engineer Gibbs. Jose, can you unmute and ask your question, please?
He is calling
Yes.
all the way from Santo Domingo.
Yes, hello, Mr. Gibbs, and thanks for the presentation. I know you love Ciudad Colonial and all the colonial town throughout the Caribbean. Can you tell us a little bit about why those colonial buildings seems to have some sort of earthquake resistance?
Many of them are made up of massive, the area of wall related to the area of floor is usually quite great in a lot of those buildings. Secondly, and there is slippage between the adjacent blocks of stone, which can have a major effect in damping, in providing damping to the structure. But some of them have collapsed and some of them have strengthened. For example, the most famous one in Santo Domingo is the El Alcázar. And that building has been significantly strengthened during the restoration work, which was done, speaking from memory, in the 1940s.
By the end of the 20th century also. It's been strengthening a couple of times.
Okay. Engineer Gibbs, following on from Jose's question, we obviously are in a region where there are several culturally sensitive buildings and structures. In your opinion, how difficult would it be to retrofit some of these monuments or structures for earthquake resistance?
Retrofitting is always a difficult and expensive job. But Italy, which is an earthquake country, is very keen on its historical patrimony. And they have many masonry buildings in Italy which are impacted by earthquakes. So in Italy, they have developed to a significant degree systems for strengthening and retrofitting those old buildings. And a lot of that information is documented in a way that's accessible in the English language. So when it comes to historical buildings in the Caribbean, and if we are keen on saving them for future earthquakes, I think we should look to Italy for our guidance. Let me say that there was a very famous and very large fortification in Iran called, in a place called BAM, B-A-M. And Iran, of course, has frequent earthquakes. And those fortifications, those castles and fortifications were centuries old. And so they lasted for centuries. And then I think it was in either 2004 or 2005, there was a major earthquake in BAM and the entire thing collapsed. So age does not mean that your building is safe, but of course buildings do age and do get weaker with aging in some cases. But clearly there's an opportunity to learn from the Italians if we want to protect our heritage buildings in the Caribbean.
Okay, I have a question from Andrew Simpson, and he's asking if fiber reinforced aircrete domed homes, if they're suitable for earthquakes. And he's asked if geodesic domes constructed from metal and cladded with PVC, if they are suitable for earthquakes.
The first one is fiber
reinforced aircrete domed homes.
Well, it sounds as if the dome is very often, doesn't have to be circular, but very often it is circular. Sounds like a very nice shape for earthquakes. And the fiber reinforced dome probably is a very, very thin shell. That's the impression I have, which means it's lightweight, which is also a good feature for earthquake resistance. As far as the geodesic domes are concerned, they're made of steel and a lightweight material. There should be no problem with geodesic domes.
Okay. No. Mr. Johnson, you have a further question for Engineer Gibbs. Please unmute. Hi, Mr. Johnson,
Hi.
you can unmute. Right.
Hi, thank you. Tony, going on about lightweight structures, therefore 2- and 3-story timber structures would be quite well behaved during earthquakes then, wouldn't they? Because they're quite flexible. But the problem is then that they could be blown away in a hurricane at the same time.
They could be made safe for hurricanes and earthquakes. It's a question of how you join the timber elements one to another. But there's quite a lot of guidance on the construction of timber structures from in North America. You know, 80% or 85% of domestic homes in North America have timber structures.
Yes, yes, I know.
Okay. All right. Is anyone wants to ask a last question before we close this evening's session? Any questions verbally or in the chat? Okay. Engineer Gibbs, any comments from you to close with?
Well, I hesitate to invite people to write to me with further comments or questions, because there's so many people in the audience. There was 111 at its peak, that I might be swamped by emails. But you can give my email to people. What I would much prefer is for people to critique my presentation so that my next presentation could be better than this one.
Very well, sir. And we could ask those persons if you do want to critique Engineer Gibbs' presentation, and you can view it again once it's put up on the BAPE website. Please feel free to feedback some information to the BAPE office, and we could always follow that information through to Engineer Gibbs so he's not swamped with too much information all at once. And we are happy to feedback Engineer Gibbs' information to you so that in your next presentation, as you said, you can tweak it accordingly. But thank you for a fantastic and informative presentation with a sprinkling of wit in there. So thank you very much for that, sir. I just want to give everyone an update on some upcoming information. So the May Technical, which is the event for next month, we're going to be looking at aerial options in engineering surveying, and that's going to be on May 18th, and that's going to be delivered by Mr. David Lewis, and it's going to be sponsored by Caribbean Aerial Photography. So that flyer will be coming out shortly, and you will be able to avail yourself of that. So we ask that you register and come online to see and learn what options are available to you with the use of drone technology. We also would like to invite you, if you would like to become a sponsor of one of our technical events. We ask that you contact the office, BAPE office, and speak to Stacy, and she will be able to tell you how to come on board. Of course, this evening's event is sponsored by CEP, and we want to thank Greg for jumping in at the last moment to make sure that we could accommodate the 100+ registrants that we had this evening. So a big thank you to Consulting Engineers Partnership Limited for that. Other upcoming events, the second edition of the Engine Room, the Barbados Association of Professional Engineers Quarterly Journal, that's going to be out at the end of May. So that's issue 2 will be out at the end of May. You can view the first issue on the website. So we ask that you certainly have a look through the first edition, and we are excited to see what Ray has for us in the second edition, which will be at the end of May. We're also asking our members, please, to log on and utilize the website. There's opportunity there for you to upload your yearly CPD. You can review the previous technicals, and it helps you to keep abreast of what's happening within the BAPE. So without further ado, I just want to thank you all for having joined us this evening. Thank you again, Engineering Fellow, the Honorable Tony Gibbs, for sharing with us your immense talent and brain power with us this evening. And we do look forward to future engagements. Thank you all for having joined us this evening. I bid you a good night.
Bye-bye.